In this video, we shall talk about Turing machines. Let's start with Turing's thesis, which states that any computation that can be done using mechanical means can be done using a Turing machine. Now, no one has suggested a problem that can't be solved by a Turing machine, and any problem that can be solved by a digital computer can be solved using a Turing machine. This is just a thesis, which can be proved or disproved. That's why it's accepted. Now, what is a Turing machine? It's an abstract model of computation. I like to think of it as a new way of thinking. It accepts languages called recursively enumerable languages. Now, for a language to be considered recursively enumerable, there must be a Turing machine that accepts it. Formally, Turing machines are defined using a 7-element tuple. Just like finite automatons, Q represents the set of states, with Q0 as the initial state. Sigma represents a set of input symbols. Gamma represents a set of symbols that are to be written onto the tape. Lowercase sigma represents the transition function. B represents the blank symbol. Now, this blank symbol is a special symbol. It's not part of the input symbols or the output symbols. This symbol represents a blank cell on the tape, which we'll discuss later in the video. Then there's F, which represents a set of final states comprising of a single accept state and a single reject state. Just like finite automata, we can represent the Turing machine mathematically using a transition table or using a transition diagram. Let's start with the transition diagram. Now, just like finite automata, states are represented using circles, and the start state is represented using a circle with an arrow pointing to it. Transitions are represented using arrows from one state to another. Then there is the accept states represented by double circles. The difference comes in with how the transitions are represented. Now, for example, some books will use this format. Some other books will use this format, which is I, O, and D, where this is the input symbols that is read by the tape. This represents the output, and D represents the direction the tape head will take. Let's talk about the tape and the tape head. The tape is used to feed the Turing machines with the input. I like to imagine it as a mechanical device like the read head or hard drive. The tape is divided into cells. Each cell contains an input symbol, and the tape head can either move to the right or to the left. If there is nothing to write or to change, the tape head will usually write what it has read. In this case, it will write on transitioning one cell to the right, it will just write 0. Now the tape head can only move one cell to the right or to the left per transition, and there is also blank cells which are represented by the blank symbol, B, represented by the B symbol as formally described earlier. Now, based on the tape, there are multiple variations of the Turing machine. There is the multi-tape Turing machine, which features multiple tapes, each with independent read and write heads. There is also a multi-head Turing machine, which has multiple read and write heads on a single tape. There is also a multi-track Turing machine, which has multiple number of cells arranged parallel to each other on a single tape. Let's look at an example. Let's consider the string L is equals to 0, 0, 1, 1, 0. Now initially the tape head will be at the beginning of the tape, and the Turing machine will be at its initial state. In this case, will be at QE. Now on reading input 0, we shall take this transition, and since we are not changing anything on the tape, we shall write what we have read, which is 0. This indicates the direction the tape head will take. So the tape head will take one step to the right. Here, on reading input 0, we shall repeat the same transition and take one step to the right again. Now here, on reading input 1, we shall take this transition onto state QO and move one step to the right. Here on reading input 1, we shall take this transition and move to the right again. Now on reading input 0, we shall take this transition so that means we shall remain in the same state and move one step to the right. Now on seeing a blank cell, that's an input represented by the blank symbol. Now that means we shall take this transition to the accept state. That means Q0 is accepted. As discussed earlier, the Turing machine can also be represented using a transition table. Just like in finite automata, inputs are the row headers, and The states are the column headers. The transitions are represented using this format, where this is the new state, this is the output, and this is the direction the tapehead will take. Now, Turing machines stop when or halt when they are at the accept or reject states. Turing machines and finite automata are very simple. They are both models of computations. They both use finite alphabets. They also use a set of finite number of states. State transitions are determined by the current state and the current input symbol. One difference is that Turing machines can write output, while finite automata can't. Turing machines can move from left to right and right to left, while finite automata can only move from left to right. A DFA is only an acceptor, while Turing machines can also do computations. Now, based on these similarities, there is the standard Turing machine, which is very similar to a deterministic finite automata in terms of the control program. There is also a non-deterministic Turing machine, which share a similar control program as a non-deterministic finite automata. In this video, we have looked at the introduction. We've talked about Turing's thesis, what a Turing machine is. We have also formally described a Turing machine using a 7-element tuple. We've also seen a description of a Turing machine using a transition diagram. We've also talked about the language of a Turing machine, and we've said it accepts recursively enumerable languages. We've also looked at various types of Turing machines based on the tapehead and the control program. We've also talked about Turing machines halting and said it halts either when it's at the accept or reject state. Thank you for watching.